Hello everyone, welcome to this lecture. So, the plan for this lecture is as follows. In this lecture, we will introduce the definition of subgroups and we will see some properties of subgroups, and then we will discuss about Lagrange's theorem in the context of subgroups and its applications. So, let us start with the definition of a subgroup. So, imagine you are given an abstract group G with operation O, it may or may not be finite, and imagine I take a subset H for the set G. Okay. Again, it may or may not be finite. Of course, if G is finite, any subset will be finite, but if G is infinite, then I may take a finite subset or infinite subset. Now, if the subset H with the same operation O satisfies the group axioms, namely G 1, G 2, G 3, G 4, then I will call H along with the operation O to be a subgroup of the original group. Okay. So, an example of a subgroup will be the following. So, imagine my group G is the set of real numbers with the operation integer addition. Then if I take the set of integers, then that will be of course a subset of the real numbers. So, my real number was the bigger group or the bigger set, and my integer is a subset of the subset of the set of real numbers, and I take the same operation plus here. So, it is easy to see that the set of integers is indeed a group, it satisfies the group axioms with respect to the integer addition, and hence I can say that this is a subgroup of the group of real numbers with the integer addition. Whereas, if I take the set of integers as my main group or the bigger group with the integer addition operation, and now if I take the subset, namely the subset of non-negative integers with the plus operation, then it does not constitute a subgroup, because this set, namely the set of non-negative integers, does not satisfy all group axioms, namely the additive inverse is negative and it will not belong, it will not belong to the set of non-negative integers. Okay. So, now an interesting question is, imagine you are given an abstract group and now I give you a subset, how do I check whether it is a subgroup or not? There are two options. Option 1, that you manually check whether all the group axioms are satisfied for the subset H that you are given, but that is not what we will prefer, because if my subset H is very large, then it might become very difficult to verify whether all the group axioms are satisfied or not. Instead, what we are looking now here is the following. We are looking for a characterization, some kind of condition which should be sufficient to check and declare whether the given subset H satisfies the group axioms or not with respect to the operation O. Okay. So, here is a very interesting characterization for subgroups. So, you are given a subset H, of course, the subset H has to be non-empty, because if it is empty it can never be a group, because you need the identity element to be present at least in your group, right. So, definitely H can't be empty, it has to be a non-empty subset. So, imagine you are given a non-empty subset, the characterization is the following. You just verify whether the two properties S1 and S2 are satisfied, and if they are satisfied, then you can declare that the subset H indeed constitutes a subgroup of the original group. By the way, I am sticking to the multiplicative notation here and I am removing the abstract operation O, I am treating it in the multiplicative sense. So, what are these two conditions? The condition S1 demands that the closure property should be satisfied. That means, you take any x comma y value from your subset H, the result of the group operation should be a member of the subset H itself. And the second property here is that every element in the subset H should have multiplicative inverse present in the subset H itself. So, the claim here is that if these two properties are satisfied, that automatically ensures that all the group axioms are satisfied. That means, I do not need to check separately for the existence of the identity element, and I do not have to check for the associative property. So, let us see the proof of this characterization. So, I have to verify, I have to prove that if indeed S1 and S2 are satisfied, then all the group axioms are satisfied in my subset H. So, let us see whether the closure property is satisfied, whether well that is given as part of the S1 condition itself. So, if indeed S1 condition is satisfied, that means the closure property is satisfied. The operation dot or the operation abstract operation O was indeed associative in the G itself, because G satisfies the group axioms. So, it will be associative in H as well, because the elements of H are nothing but the elements of G, right. And closure property is anyhow satisfied, guaranteed in H. So, that means the operation O or the operation dot will be associative in H as well. The axiom number S2 guarantees you that every element in H has its inverse in H present, and now I have to show that the identity element is also a part of my subset H if the condition S1 and S2 are satisfied. So, for that consider an arbitrary element x belonging to your subset H. I can apply the axiom number S2 and claim that X inverse is also present in H, and from the first axiom S1 I know that the result of X operation X inverse will be an element of H, because the axiom number S1 says that the closure property is satisfied. So, X is an element of H, X inverse is also an element of H. So, the result of group operation of X and X inverse should be also a member of H, but what is the result of group operation being performed on X and X inverse? It will be the identity element, and this shows that the identity element is guaranteed to be present in my subset H. So, that shows that if S1 and S2 are satisfied, all the group axioms are satisfied. Okay. So, that is a very nice characterization. Now, an interesting corollary here is the following. The corollary says that if your original group G is finite, then no need to check even for the second axiom, just check whether the first axiom is satisfied or not, namely just check whether the closure property is satisfied or not in your subset H. If the closure property is satisfied in the subset H, that automatically guarantees you that all the remaining group axioms are also satisfied in your subset H. So, the proof for this corollary will be the following. What essentially we have to show is the following. We have to show that if your bigger group G is finite and if your condition S1 is satisfied in H, I have to show that condition S2 is also satisfied in H, because we had already proved that if both S1 and S2 are satisfied in H, then all the 4 properties of group hold in H. Right now, it is not given to me whether S2 is satisfied or not, it is just given to me that G is finite and S1 is satisfied in H. I will show that if G is finite and S1 is satisfied in H, I can draw the conclusion that even S2 is satisfied for my H. And now, if S1 and S2 are satisfied for my H, I had already proved that all the group axioms will hold for H as well. So, everything boils down to this proof. Okay. So, the proof will be divided into 2 cases depending upon what is the cardinality of your subset H. If the subset H is a singleton set and it has the identity element only, right. So, if at all it has to be a subgroup, and if it is singleton set, it has to have the identity element. So, consider the case when indeed the subset H is singleton and it has the identity element, then I do not have to check S1 holds, S2 holds or not. Indeed they hold, because indeed this subset H which has the identity element only present in it along with the group operation is indeed a subgroup, because the closure property is satisfied, because if you perform the group operation on the identity element with itself, you will obtain the identity element which is again a member of H. The operation O will be associative anyhow in H. The inverse element of the identity element with the will be the identity element itself, and anyhow the identity element is present in H. So, it trivially constitutes a subgroup. I do not have to check about S1, S2. On contrary, not contrary. On the other hand, imagine that your subset H is not a singleton set. Okay. So, imagine that it has some other elements and consider one such element x which is different from your identity element. Now, since x is a member of H, x is a member of G as well. So, let the order of x be m, and when I say order of x, it means order of x in the context of the group G. That means, if the order of x is m, that means m is the smallest positive integer such that x to the power m is the identity element. Okay. Now, if x to the power m is the identity element, if I multiply both the sides of this equation with x power minus 1, and again x power minus 1 is a group element as per my definition of the group exponentiation. If I multiply both the sides with x power minus 1, then the identity element operated with x power minus 1 will give me x power minus 1 only. That means, I can say that x power minus m minus 1 is same as x power minus 1. Now, what is my goal? My goal is to show that if S1 holds in my subset H, then S2 also holds. So, that is what I am trying to do here. I have taken an arbitrary x here different from the identity element whose order is m, and right now I have derived that x power minus 1 is same as x power m minus 1. My goal is to show that x power minus 1 indeed belongs to the subset H. So, to show that x power minus 1 indeed belongs to the subset H, I have to equivalently show that x to the power m minus 1 belongs to the subset H, because I have already proved here that x to the power minus 1 is same as x to the power m minus 1. And now, how do I prove that x to the power m minus 1 is a member of this subset H? I can repeatedly apply the fact that axiom S1 holds in my subset H on the element x. So, remember x is a member of the subset H, and if S1 holds, it holds for x as well. So, x square will be a member of H, x cube will be a member of H, x 4 will be a member of H, and hence x power m minus 1 also will be a member of H, and x power m minus 1 is nothing but x power minus 1, and that shows that x power minus 1 is automatically guaranteed to be present in H if the axiom number S1 is satisfied. Okay. So, now you might be wondering where exactly the fact that G is finite is used here. Well, the fact that G is finite is used here is when I use the fact that the order of x is m, because if G is infinite, then I can't say necessarily what exactly is the order of x, it may not be defined at the first place, right. So, that is why this proof holds only for the case when my group G is a finite group. So, that means if I am given a finite group G and a subset of G, then to check whether the subset H constitutes a subgroup or not, it is just sufficient to check the closure property. Just check whether the closure property holds in the subset or not. If it holds, then you can conclude that all the remaining group axioms will also hold. A very nice characterization, right. So, now based on this we will generate various cyclic subgroups of a group. So, you might be given a group which need not be a cyclic group, but by using the previous result I will try to now derive cyclic subgroups of my original group. Okay. So, I have retained the result that I have just proved, namely the characterization for the existence of a subgroup. That means, if you are given a non-empty subset, how do you check whether that non-empty subset is a subgroup or not. So, now imagine you are given a group G and an element x whose order is m. Its order is m means x to the power m is the identity element. That means, m is the smallest positive integer such that x to the power m gives you the identity element. Now, let me define a subset H which is obtained by raising or by computing m distinct powers of x, namely x to the power 0, x to the power 1, x to the power m minus 1. So, these are m elements. Okay, and all of them are distinct. We had already proved that in one of our earlier lectures. Now, my claim is that this subset H is a cyclic group whose generator is X, okay, and it is a cyclic subgroup of your original group. So, how do we prove? So, first of all, X is a generator, that is easy to see because all the elements of H are generated by different powers of X. So, indeed X is a generator. Now, I have to prove that indeed the group axioms are satisfied for my subset H, and for that I have to show that both property S1 as well as property S2 holds for H. If I can prove S1 and S2 holds for my subset H that I have computed like this, then that shows that H is indeed a cyclic subgroup. So, let us first prove the closure property. So, let us take two different elements from the set H. Since they are two different elements of H, they are basically some distinct powers of the generator X, say the ith power and the jth power. Then I have to show that the group operation performed on x power I and x power j will also give me an element of H, and that is very trivial to prove because the group operation performed on x power I and x power j will give me an element x power I plus j. Now, this x power I plus j is same as x power in the exponent I plus j modulo m. Why so? Because since the order of x is m, that means x power m is 1. So, I can rewrite this x power I plus j as several blocks of m power 1, m x power m, x power m, x power m, x power m, and a last block which may not be a full block of x power m, but rather it will be I plus j times modulo m. Okay. Now, I know that each block of x power m will give me the identity element, and the last block which has x power I plus j modulo m, that will remain. Now, the identity element being multiplied to itself several times will give me the identity element. So, this will be same as identity element being multiplied with x power I plus j modulo m, and hence the result of x power I plus j is same as the result of x power in the exponent I do I power I plus j modulo m. But then I plus j modulo m will give you a remainder in the range 0 to m minus 1. Okay. So, this will be a value in the range 0 to m minus 1, because the possible remainders that you can obtain by dividing I plus j by m will be either 0, 1 or m minus 1. That means, this is nothing but some power of x in the range where in the exponent is in the range 0 to m minus 1, and that will be definitely an element of H, because any power of x where in the exponent you have something in the range 0 to m minus 1 will give you an element of H. So, that shows the closure property or S1 is satisfied. Now, I have to prove the S2 property, that means, if I take any arbitrary element from the subset H that I have computed, it has an inverse present in the subset H as well. Okay. So, I take some arbitrary element where the arbitrary element is x power I and I is greater than 0. Why greater than 0? Because if I is 0, then x power I is nothing but the identity element, and the inverse of the identity element will be the identity element only. So, S2 will be of course satisfied for the identity element. I want to prove that it is satisfied for any other non identity element as well. So, that is why I am taking x power I where I is not 0. Okay. And I have to show that for this x power I element, the corresponding inverse is also present in H. Okay. So, my claim is the following, that x power m minus I, which is also an element of the subset H, constitutes the inverse of x power I. So, it is easy to see that indeed x power m minus I belongs to H. Why? Because I is some power, of course, I is greater than 0, but I is also less than equal to m minus 1. That means, m minus I will also be now a power in the range 0 to m minus 1. So, that is why it is a member of H, And what will be the result of performing the group operation on x power I and the element x power m minus I? Well, it will be the same as identity element. So, that is why I can now conclude that you take any non-identity element in the subset H, its corresponding inverse is also present in the subset H. And since S1 and S2 is satisfied for the H that I have built, that means H indeed constitutes a group, and it is cyclic because its generator is X. By the way, you might be wondering that why I am verifying both S1 and S2 here for the subset H. Why can't I just verify S1? Because I just proved some time back that it might be sufficient to just check the condition S1. Well, that is the case when your group G would have been a finite group, but here I am proving the property for a group G which may or may not be finite. So, if your group G is not finite, then I have to check for both condition S1 as well as condition S2. Okay, that is why I am checking for both S1 and S2. Right. Now, let us next define what we call as left and right coset of a subgroup, and this notion of cosets is very important when we perform error correction in coding theory. Of course, we will not be discussing coding theory in this course, but people who are familiar with error correcting codes, they might be knowing that when we perform error correction, then we use this concept of left and right cosets. So, let us define what exactly is a coset. So, imagine you are given a group and a subgroup for the group. Again, they may be finite, infinite and so on, because the definition does not put any restriction. And imagine you are given a group element small g from the bigger group. Then the left coset of the subgroup H. So, the cosets are defined with respect to your subgroups, but they are defined with respect to elements which are chosen from the bigger group. So, element, it might be the case that the element small g may not be a member of H. It may be present in G, but not in H, right. That is not. So, definition does not put any restriction that element small g should be a subset should present in the set H. It may or may not be present, but the cosets are defined with respect to your subgroups. So, the left coset of the subgroup H is denoted by this notation G times the subset H, and it is basically the collection of all group elements which I obtain by performing the group operation between the G that I have chosen here and all the elements of my subgroup H. So, you can imagine the following: this is your H, okay. Call the elements as H1, H2, it might have infinite number of elements, and you have the element G which you have picked. So, you perform G operation H1, you perform G operation H2, you perform G operation HI, you perform G operation every element of subgroup H. Of course, from the closure property you will obtain group elements. The collection of those group elements is your left coset. Why left coset? Because G is operating, or G is acting as your left operand, and H or the elements of the subgroup H are occurring as your right operands, whereas the right coset is defined similarly, but what you now do is the elements of subgroup H will occur as your left operand, and each of them will be operated with G. That will be your right coset, and the notation for that will be this H time G. Okay. Now, if you change your element G, that will give you a different left coset and a different right coset, right. So, it is not the case that you will obtain the same left coset and right coset every time, it depends. So, we will now we will soon see very nice characterization, nice property of the left and right coset, but this is the general definition of the left and right coset. So, the first thing that we can prove here is the following: if H is a finite subgroup, then you take any element from the bigger group, the corresponding left coset, right coset, they have the same cardinality as the cardinality of your finite subgroup, and the proof is very simple. So, imagine your finite subgroup H has n number of elements, and the left coset will have the elements g times h1, g times h2, g times hn. So, I am again using mathematical notation when I am saying g times h1, but you can treat it as g operation h1, g operation h2, g operation hn. And remember, from my right cancellation rule, all these elements g operation h1, g operation h2, g operation hn, they are distinct. Namely, you can't have g operation hi giving you the same result as g operation hj, where hi and hj are different, because if that is the case, you can apply the left cancellation rule and come to the conclusion that hi is equal to hj, which is a contradiction. So, sorry for the typo, it should be left cancellation rule. Okay. So, that is a trivial proof. Now, let us see a very nice property here regarding the cosets. So, let me first demonstrate the property and then we will prove it for any general group and general coset. So, let me take this group G, which is the set Z11 star, and remember the set Z11 star will have all the integers in the range 0 to 10, which are co-prime to my modulus 11. So, basically you will have all the integers 1 to 10 except 0, because 0 is not co-prime to 11, and my operation is multiplication modulo 11, that is my concrete group operation. And suppose I take the subgroup consisting just of elements 110. If you are wondering whether this is a subgroup or not, well, you can apply your characterization S1 on this subset H, and then you can verify that indeed the characterization or the group axiom S1 or the property S1 holds for this subset H. Okay. Now, let us compute the various left cosets of this H. By various left cosets mean I will keep on changing my G. I will take G to be 1 first, and then I will take G to be 2 next, and then finally, I will take G to be 10. So, the left coset of H with respect to 1 will be 1 comma 10. The left coset of H with respect to the group element 2 will be 2 comma 9. Why? So, this will be because of the following reason. So, if I take G to be 2, then G times H will be basically 2 times 1 modulo 11 and 2 times 10 modulo 11, because my operation is multiplication modulo 11. So, 2 into 1 will be 2, 2 modulo 11 will be 2, whereas 2 into 10 will be 20, 20 modulo 11 will be 9. So, that is why this left coset is 2 consisting of the elements 2 comma 9. In the same way, you can compute the left coset with respect to the element G equal to 3 with G equal to 4. So, you will have 10 cosets, okay, because you have 10 possible values of G. But now you can see here, it is not the case that all my 10 cosets that I have obtained here, they are all distinct. Some of them are same completely, or otherwise they are completely disjoint. So, for instance, the left coset of H with the element with respect to the element 1 and the left coset of the same H with respect to the element 10 are same. Whereas, if I consider the left coset of H with respect to element 1 and the left coset of H with respect to 2, they are completely disjoint, they are nothing common. So, now you might be tempting to prove whether this is the case with respect to any coset or not, or is it the case that it is happening only for this G and only this subgroup. Well, that is not the case, we will prove that this is a general result. So, what we are going to prove here is the following: if you have given any group and its subgroup, then you take any two elements from the parent group, call it G1, G2, then the left coset of H with respect to the elements G1, G2 will be either completely same or they will be completely disjoint. Okay, that is a statement here. And before going into the proof idea, let us try to recall a concept that we had earlier seen in our course, where we come across a similar situation, where we proved something of the following form, that you have many subsets and either two subsets are exactly same or they are completely disjoint. Namely, we proved that result in the context of equivalence classes. So, if we have an equivalence relation and we form the corresponding equivalence classes, then we know that two equivalence classes will be either completely same or they will be completely disjoint, and that is what something similar that is happening here. So, that is why we are now going to prove this result by defining a very nice equivalence relation and proving that left cosets are nothing but equivalence classes with respect to that equivalence relation that we will define. So, my equivalence relation that I am defining here is the following. I say that element x is related to the element y if the element y is present in the left coset of the left coset with respect to the element x, right. If that is the case, I will say x is related to y, otherwise x is not related to y. And I will prove very soon that indeed this relation is an equivalence relation, namely it satisfies the reflexive property, symmetric property and transitive property. Assume for the moment that it is indeed the case, that means this relation is an equivalence relation. Then what can I say about the equivalence classes of this relation? Well, I can use the property that equivalence classes constitute a partition of your original set. So, the original set over which the relation is defined is my set G, because my x and my y are elements of G. I have defined a relation over the elements of my group G. I say element x and element y of the group G are related if y is present in the left coset of x. So, if at all this relation is an equivalence relation, then this relation, the equivalence classes will constitute a partition of this group G, and it is easy to see that the equivalence classes here are nothing but the cosets, right, because that is how I have defined here my relation, and that automatically proves that the theorem statement that we want to prove here holds. That means, either two cosets which will be completely different, or that means they will not have any overlap, or they will be completely same because they constitute your equivalence classes. So, now proof boils down to proving that this relation is indeed an equivalence relation. Okay. So, let us prove that this relation is an equivalence relation by proving the reflexive, symmetric and transitive properties. So, let us first prove that the relation R is reflexive. That means, we have to prove that every x is related to itself. That means, we have to prove that every x is always present in its left coset, where x is an element of your parent group. So, this simply follows from the fact that x is always the result of group operation being performed on x and the identity element, and this identity element is of course an element of your subset H, because H is a subgroup. So, that means, when I will be forming the left coset of x, I will be encountering the element x operated with identity element, and that will give me the element x itself. Hence, I get the conclusion that x is related to x, showing that my relation is reflexive. Now, let us prove my relation is symmetric. So, imagine x is related to y. X is related to y means, when I operated x with all the elements of H, I must have encountered some H1 such that x operated with H1 would have given me the element y. Okay. Now, if this is the case, then I can say that x is nothing but y operated with H1 inverse, right. How? If I multiply both the sides of this equation by H1 inverse, then I get that x is equal to y operated with H1 inverse. But since H1 is a member of subgroup H, the H1 inverse also will be a member of subgroup H, it will be some other element of the subgroup H. That means, I can say that x is nothing but y operated with some element of the subgroup H, say H2. So, I am calling H1 inverse as H2, but y operated with H2 will be nothing but a member of the left coset of y. So, what I have shown here is that the element x belongs to the left coset of y, and if element x belongs to the left coset of y, then that is equivalent to showing that y is related to x, as per my definition of relation R. So, I have proved that my relation is symmetric as well, and in the same way I can prove it is transitive. So, imagine x is related to y and y is related to z. I have to show that x is related to z. So, if x is related to y, that means y is a member of left coset of x, that means y is some x times h 1, where h 1 is a member of my subgroup H. And if y is related to z, that means z is a member of left coset of y, that means z is equal to result of y operated with some h 2, where h 2 is a member of my subgroup. Then by plugging by tying these two facts, I obtain that if I substitute the value of y here, I obtain that z is the result of performing the group operation on x and the result of group operation being performed on H 1 and H 2. But since both H 1 and H 2 were members of my subgroup H, I can apply the closure property and say that H 1 operated with H 2 will be some element H of the subgroup H. Hence, I say that Z will be a member of my left coset of x, that means x is related to Z as well. So, that shows my relation R is transitive as well. Okay. Right. So, now given the definitions of cosets, we will give a very nice theorem which we call as Lagrange theorem, which will be useful later on. The Lagrange theorem in the context of group is the following: if you are given a finite group whose order is n, namely there are n elements in the group G, and say H is a subgroup, of course, it has to be finite because my parent group is finite, and say the order of the subgroup is m, namely there are m number of elements in my subgroup H, then the Lagrange theorem says that m divides n. Why this theorem is for finite group? Because if it is not for finite group, I can't say anything how many elements are there in G, and my H also could be an infinite subgroup, right. So, basically Lagrange theorem says that the order of any subgroup divides the order of parent group if your parent group is finite order. And the proof is very simple, assuming that we have already proved the result regarding our cosets. Now, since my subgroup size is m, that means the cardinality of H is m, the size of each coset will be m, because we proved already that the size of each left coset is same as the size of your subgroup, and since the size of subgroup is m, the size of each coset will be m, and we had already proved that the cosets constitute a partition as per the relation that I have defined here. So, now if there are k distinct cosets which you can form all together, right. So, your G will have n number of elements. So, call the elements as G1, G2, Gn, and you may form the coset G1 times H, G2 times H, Gn times H. It may not be the case that you obtain n distinct cosets, some of them may be repeated, right, because they might be same, or it might be the case and or otherwise the two cosets will be completely different. So, imagine that all together they constitute k distinct cosets. Okay. Now, in each coset you have m number of elements, and if you have altogether k distinct cosets, since the union of all the cosets, distinct cosets will give you the original group G, the parent group G, I can say that k times m is nothing but the number of elements in your parent group n, and that shows that m divides n. Okay. A very simple proof. Okay. If there are other ways of proving the Lagrange theorem, but they might be slightly long, but once we have proved the general result regarding cosets, the proof is just 2-line argument here. Okay. Now, let us see some interesting conclusions of this theorem. So, imagine if your G is a finite group of order n, and if you take any element from the group, then the order of that group will divide the order of the order of that element G will divide the order of the group, namely n, namely G to the power, and the second conclusion here is that G to the power n is also identity element. Okay. And the proof again is very simple. So, imagine we construct a cyclic subgroup H by taking different powers of the element G. Why it will be cyclic subgroup? We have already proved few slides back that if you take any group element from the parent group and compute different powers of that element, it will give you a cyclic group. So, imagine I constitute the subgroup H by taking different powers of the element small g, that will give me a subgroup, and say the order of the element small g is m. Well, if the order of the element small g is m, then the number of elements in the subgroup H that I have constructed will also be m, because I have constructed H by computing g power 0 up to g power m minus 1. That is my cyclic subgroup that I have constructed. But what exactly the Lagrange theorem says? If you have a finite group and a subgroup of that, then the order of the subgroup always divides the order of the parent group. So, what is the order of the subgroup? I have m, and what is the order of the parent group? I have n. So, from the Lagrange theorem I obtain that m divides n is completely divisible by m, okay. And that shows that the order of my element G has to divide the order of the bigger group. Now, the order of the element G might be m, and where m can be strictly less than n, but the second result that we want to prove here is that G to the power order of the group will give you the identity element, and once we have derived this fact, it is very easy to prove that. So, let us see what exactly we will obtain if I compute G power n. G power n will be nothing but G power k times m, and since the order of the element small g is m, I know that G power m will give me the identity element, and identity element raised to power k will give me the identity element. Okay. So, that is an implication of the Lagrange theorem, and if I apply this implication in the context of a prime order group, namely a group where I have prime number of elements, then I get the fact that it will be cyclic, and every element other than the generator element will be every element except the identity element will be a generator for that cyclic group, if my group G is a prime order. Why so? Because if my group G has prime number of elements, okay, and if I consider an arbitrary element x and try to generate the subgroup through that element x, the order of that subgroup has to divide the order of the parent group, but the parent group has order p, which is a prime quantity, prime value, and the only divisors of a prime number are 1 or p. But since the x that I have chosen is not the identity element, the only option that is left is that the order of the x is the prime number p itself. And if the order of the x is the prime number p itself, that means the subgroup that I have generated through x is nothing but the whole parent group, because if the order of x is prime number p and the parent group's order is also prime p, that means through x I have generated all the p distinct elements of my group, right. So, that is a very powerful result. That means, if you want a cyclic group where you do not want to worry about searching for the generators, then try for a group which has a prime order. So, that with that I end today's lecture. These are the references. Just to summarize, in today's lecture we discussed about left cosets, right cosets, we derived several properties for the cosets, and we also discussed about subgroups. We gave a characterization for subgroup, and we also discussed properties regarding the order of the subgroups, namely the Lagrange theorem. Thank you.